Okay, good morning, class. You're on to Mamu with Jarvis, the mathematics multiverse. Today we'll be looking at our grade 10. Grade 10 is not on the board, so let's do that quickly. Grade 10. This will be our grade 10 class. But one of the things I have tried doing over the years is to try to ensure that my videos can be watched by anybody at all, anybody. I try as much as possible. I keep that intentionally in heart when I do my videos, that anybody can watch. Depends on your IQ level, depends on your interest. All you need to enjoy my videos will just be interest. This morning, looking at our grade 10 arithmetic. Arithmetic, we'll be looking at a matter called standard form and logarithm. In most textbooks, you wouldn't see it this way. You will just see indices and logarithm. But I have chosen to break them because indices tends more towards algebra and logarithm tends more towards arithmetic. So to bring in perspective as we study, this is coming as a function of recent researches I'm doing on my own. I try as much as possible to show you the different aspects as you go so that you can make informed decisions on how these things all connect. Our textbook of reference will be, for this particular class, will be the New General Mathematics for SS1. We're on page 19. If you check that textbook, you discover that it's called, that chapter is called Indices and Logarithm. But what I've done here is to break it. So I'm going to focus on logarithm as a topic under arithmetic. So let's get down to work quickly. I've done lots of videos on this matter of standard form. But it's always important for a teacher that when you come into a new topic for students or a new learning environment, you try as much as possible to reiterate the ideas you have sold before now. Now, what is standard form? Standard form, for me, would mean that I have a decimal fraction that I want to make a unit decimal. And the only way I can connect a decimal fraction with a unit decimal is that I need to talk about the number of movements I have made. So I'm going to write something on the board and I'll use that as a basis to explain this idea, this big grammar, these big things I've been talking about. I'm going to sit on the board now. Now look at this. If I say, let's start with a number you're very used to, 24. Now, 24 is not just 24. This is 24 as a whole number. 24 only exists because it is 0.0. There is something here that is not necessary, so I don't talk about it. So 24 can be written as 24.0. Now, I cannot write, this is what is called a decimal fraction. Now, I cannot write 24 as a unit decimal. What is a unit decimal? A unit decimal is any decimal where the highest digit you can perceive is the unit. That's why it's called unit decimal. Perceive only unit in this decimal. So what would I do? If I'm going to write this as a unit decimal, it will simply be what? 2.4. Unit being the highest decimal. Unit being the highest whole number parts. Because for every decimal fraction, you will have two parts. You have what is called the whole number part. I have what is called the decimal fraction part. Do you understand? So that's what makes a decimal fraction. You have the decimal fraction part, you have the whole number part, but technically we call them all decimal fractions. So if you look at this, 2.4 times, what did I do to get 2.4? I can move backwards. If I move backwards, I've moved one decimal place to the back. And that will be 10 raised to the power of, how many movements have I made? 1. Now, technically, when you're moving backwards, you are trying to make small what was big. When you're moving decimals forward, you're trying to make big what was small. So that's why if you remember your primary school, say if you're moving your decimal places forward, what's happening is that you'll be having negative because you're trying to make something that is small big. But if you're moving backwards, you're trying to make something that is big to become what? Small. So that's for decimal fraction, and that's for your unit decimal. So this is your unit decimal. And this is what we call your movement. So that's 10 raised to the power of 1 is your movement. So the movements you have made. So usually if in my concept development, I will say D subscript F will be equal to U subscript D times 10 raised to the power of what? Movement. So this is my own description of what is standard for me. So writing the number this way becomes the way you write standard form. Now, I will take another example. For instance, if I have 225.32, this will simply be what? Or let's take a bigger number. And I have to write this as a unit decimal. First thing, I will just write this units and then decimal. The next thing I'll do is to count how many decimal places have I moved. If you look at this, 1, 2. So that will mean that I've moved 2 decimal places. And that will mean that I have made 2 positive movements. Because I said that if you move backwards, you've moved what? 2 decimal, you've moved 2 positive places. If you move forward, you have moved 2 negative places. All right, so that's for that. And to further help us in this course, there is an exercise here on page 19 of this textbook, on 19 of our New General Mathematics. And it says, express the following numbers or express the following in what? Standard form. I'm going to give us a few seconds to do that with your textbook, page 19, exercise 1G. We're going to do that quickly and then we'll see questions of this nature. You shouldn't spend more than, we have 20 questions here and you should not spend more than 5 to 10 minutes doing this. You should be able to do this in 5 to 10 minutes. If you spend more than that, then we need to see how we can help you get this done better and quicker. So I'm going to leave you for 5 to 10 minutes to do that. I will be back. Okay, to drive home the concept of this topic, the standard form aspect of it, we'll be looking at exercise 1G of our text. Now, I wouldn't solve all. I'll just pick a few of the questions that I think will pose an issue to us. So I'll look at number 1. Look at number 1. It says 4.35. We're required to write this in standard form. Remember, we said that standard form has to do with what? The unit decimal. If you look at this number carefully, it's already a unit decimal. So we don't need to make any movement. So the best thing to write is just to say 4.35 times 10 raised to the power of 0. Because if you recall from our algebra class, we said that 10 raised to the power of 0 is what? 1. Where 10 raised to the power of 0 is equal to 1. And it works true for all numbers, especially, except where you have a is equal to 0. So if I say a raised to the power of 0 is equal to 1, put in perspective. Now, this will be true for as long as this a is not 0. I've told us with time, you get to understand why that one is like that. So if I have 4.35 to standard form, I have not made any movement. So that will be what? 10 to the power of what? 0. Now, number 2. Number 2 says 0.788. What would it be equal to? 0.788. Now, if you look at this, this is a small number. A number that is less than 0 is small. A number that is greater than 0 is big. Just to keep a perspective for this matter of standard form. Now, what would be the unit decimal here to go 7.88 times? How have I moved? You discover that 7.8 will mean that I bring a decimal point here. So I have moved from here to here. I'm trying to make a small number big. So I would have made a negative movement. So that would be 7.88 times 10 raised to the power of what? -1. All right. The next crucial one is question 5. 06.7. This one appears tricky, but your knowledge of place value system will help you out here. Recall that this is the same thing as 6.7. This 0 means that there is no digits, 6 units, and 7 tenths. So you don't have any business with this one. So this is a number being given to you. So if you look at that, this will be what? 6.7 times what? This is a unit decimal. So what it means is that you've not made any movement. So that will be what? 10 to the power of what? 0. So I've not made any movement. So that will be what? 10 to the power of what? 0. All right. So that takes care of that. Okay. Okay, so the next one we may want to look at is question 15. Like I said, I'm not going to solve all. I will just emphasize the ones that could be a problem to us. Number 15. Now, if you look at number 15, it says 9. What is 9? Remember that I told you, if you remember from this example, one of the examples I gave, 9 is essentially what? 9.0, meaning 9 units and no tenths. So we said that we will not try to write this as its unit decimal form. And it means that there's no movement here. And that will be what? Times 10 to the power of what? 0. So these are the ones I think would pose an issue to us. Interesting enough, I've already done this before. So I will drop the link when I post this video. I've done this, I've solved everything here before now, but I'm just trying to focus on those questions that could pose an issue to us. So having said this, we can now move into logarithm proper. Okay, so we come to the matter of logarithm, and as is a practice, you can't do logarithm properly without understanding your standard form. You're going to see the beauty of what we've done by the time we go into logarithm. Now, what is logarithm? Logarithm is indices. I want that to sink. Logarithm is also what? Indices. What is the log of a number? The log of a number is the power to which a number is raised. So I'm going to write that on the board for you to see. The logarithm of any number x is the power a to which or by which the number x is raised. So if I have the logarithm of any number x is the power by which the base, a given base, sorry about that, a given base, let's call that y, is raised. So what does that mean technically? It means that x will be equal to what? Y raised to the power of e. So this a here is the logarithm. So the logarithm gives us an idea from our indices on how many times a certain base is multiplied. So you discover that whenever we mention logarithm, technically we are talking about the behavior of the index. So synonyms, words used as synonyms now. If you say logarithm, if you say indices, if you say power, you mean the same thing. So the logarithm of a number, that is why much later you discover that when you add number, when you multiply numbers, you are adding their logs. When you divide numbers, you are what? Subtracting on logs. You get it? So I want you to have this understanding as we start the topic. Our focus in logarithm will not be on the laws of logarithm, because those laws we would want to add up to the algebra aspect. Our focus in this aspect of logarithm is to focus on the use of tables. Use of what? Logarithm tables. So there's something we call logarithm tables. And that's what we'll be using to solve problems here. Focus on our use of what? Logarithm tables. So we're going to focus on the use of logarithm tables, and that's what we'll be using to solve our problems. All right, so very cool. So what we need to do first of all is to understand the behavior of a log. So I will start by trying to look at a few numbers. If you go to page 20 of your text, go to page 20 of your text, you're going to see a few of the questions. And then page 21, actually, I'm going to focus on, I'm not going to follow the order of the book. I'm going to focus on question number 4, the exercise 1H of this textbook, exercise 1H. And we're going to look at question number 4. I'm going to use question 4 to drive an important concept. Now, first of all, let's start by doing something. There are different bases we can use to describe logarithm, but when we want to use logarithm table, we use base 10. We use base 10. So everything I'll be talking about in logarithm now will be that I am working with what? Or working on what? Base 10. Let me start with a simple example. Now, you can be asked to say, find the log. Some people say logarithm, log for short. The logarithm of 54. Find the logarithm of 54. So, how do you solve this? Now, this is what you're going to do. You simply say 54 will be equal to, you write this in standard form, will be equal to what? 5.4 times 10 raised to the power of what? Now, remember that for any whole number, there exists an invisible point in front of it. So from that point, you move backwards. So that'd be 5.4 times 10 raised to the power of what? 1. I made one movement back. So that will mean that it is 10 raised to the power of what? 1. You see that the logarithm aspect is already forming out. The next thing we need to do now is to go to our logarithm table. Go to our logarithm table. And to make work very easy for us, if you go to page, let's confirm where that page, if you go to page 251 of this textbook, what you have there is what is called the logarithm of numbers. So when you go to that table, look for where you have 51. You're going to see on that table, you're going to see X on the top. I should have that on my screen so you can have a perspective to it. If you look at that, that will not be very clear. If you look at the table, you're going to have, or you see a normal logarithm table, you see logarithm of numbers. You're going to see X. You're going to see on the heading, you're going to see X, then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then added to that, you're going to see on the vertical column, you're going to see 10, 11, as the case may be. Now, if you're saying that, if you go down on that page, you're going to see 54. That's one of the reasons why when we express numbers, if you notice, I said that for a number 54, it's actually technically what 54.0. So if you go to that table, look for 54 under the column of 0. You discover that you're going to have 7324. I don't know if you're seeing that. 7324. That 7324 is actually 0.7324. So with that understanding, My next line will now be, what then is the log of 54? The log of 54 will simply be what? Because I told us earlier that I'm working, the logarithm here is to base 10. Anytime you're using your 4-figure table or your logarithm table, you're working to base 10. So the log of 54 will simply be what? Okay, let's even help you a little more. We said that the log of a number is the power to which a given base is raised. So in this arrangement, this thing will be what? 10 raised to. So this will be 10 raised to the power of 0.7324 times 10 raised to the power of 1. From your knowledge of indices, if you multiply numbers or bases, what are you doing to their log? What are you doing to their index or their log or their power? You are adding them. So 1 plus this will now be what? 10 raised to the power of what? 1 plus 0.7324. And that will give me 10 raised to the power of 1.7324. So that's what this answer is going to be in this format. Another format you can have would be the log of 54 will be equal to what? Once you've written out the standard form here, you must do this line first. What is this? 1 point. Use your logarithm table. You find this one now, that will be 7324. All right, so that will now be the answer to that question. I'll give you one to do. Find for me the log of, let's say, 245. Let's see how you do it, how you cope with that. So what you need to do is, first of all, to write this in standard form. So 54 will be equal to what? Sorry, 245 will be equal to 2.45 times 10 raised to the power of what? Remember, for every whole number, there exists a decimal point in front here. So I move 2 steps backwards. 1, 2 to obtain my unit decimal. And that will be to the power of 2. Now, when I want to check my 4-figure table, my logarithm table, you discover that on your logarithm table, the first 2 digits are given. So it is the first 2 digits is what you are going to check under the 3rd digit. Is that clear? So 24 under 5, what would that be? 24 under 5, that would be 3892. And that's actually what? 10, but that's the base we're considering. 0.38 what? 38 what? 3892 times 10 raised to the power of what? 2. So this will give us 10 raised to the power of 0.3892 plus 2. And that will be 10 raised to the power of 2.3892. So that's what the final answer is going to be. 10 raised to the power of 2.3892. So that's what that one will be. So we quickly take on the next one. Okay, before that, we said that this one way to express this. We can also express this as the log of 245 will be equal to what? 10 raised to the power of what? 2 times this other one we have gotten. Do you understand? Am I getting that right? Oh, sorry. It will be equal to what? What would I get? This number here, 2, plus. What did I get when I used my logarithm table to read out this? 0.3892. 0.3892. Right? So that's what, then this will now be what? 2.3892. Now, we come to the next one. It says the log of what? 34.34. What would that answer be? What would that answer be? Now, this one is a little tricky, but we can also handle it. We start by writing this first in standard form. Take note of where the decimal point is and take note of where you are going to as unit decimal. So this will now be what? 3.434 times 10 raised to the power of what? 1. Times 10 raised to the power of what? 1. So once you've written this one out, once you've written that one out, the next thing you want to do is to say, I go to my 4-figure table. I'll check for 34 under 3. You know, the first 2 digits under the 3rd digit. But I still have 4. What do I do with that 4? If you go to your table, there's somewhere that is written what? Differences. Are you seeing it? There's somewhere they're written differences. So that differences you're seeing is where you're going to check these digits. So to make it easy for you, I tell students that you don't make a mistake. Use your 4-figure table, look for 34. I will be doing another video on this, on the use of this table. I'm going to do another video where I'll write and be showing you how the 4-figure table goes. But so if you have any issues with this class, know I'm doing another video to help you understand this better. Now you go to your table, you look for 34 under 3. So I'll look for 34 under 3, and I'm seeing 5353. Confirm 5353. So I'm going to write this here somewhere in my book, 0.5353. And along that path, I will trace to where I have difference of 4. If you've done the tracing right, you're going to see 5. Now that 5 is interpreted as adding to the last digit of this decimal you have. You don't need to write 000, no. You just know that 5 is added to the last digit. If you have a 2-digit number answer, you add it to the last 2 digits, and then you add up. This will be 8, 5, 3, and 5. So that's 0.5358. All right. So now you will then change this to 10 raised to the power of what? 0.5358 times 10 raised to the power of 1. So this will be 10 raised to the power of 0.358 plus 1. And that will be 10 raised to the power of what? 1.5358. Now, the question somebody is asking is, how is it possible that I know that this answer is correct? And I'm going to show you that now, because I wanted to do these examples before I show you another idea. We had learned from indices that 10 raised to the power of 0 is equal to what? 1. Is that not? 10 raised to the power of 0 is what? 1. Now, 10 raised to the power of 1 is what? 10. So 10 raised to the power of 0 is 1. And 10 raised to the power of 10 raised to the power of 1 is 10. So, if I'm looking for the log of a number, now let's watch you. Or let's put it in another, so that you can get perspective to it. 10 raised to the power of 0 is 1. 10 raised to the power of what? 1 is 10. 10 raised to the power of 2 means 10 multiplied twice, and that will be what? 100. So if I have a number like 7, you already see what the log will look like. The log will be between, the log of the number will be between what? 0 and 1. If I have a number like, let's say, like what we have done now, let's say, okay, let's even use 200 and, or let's use, what's the number? Okay, let's say 34. You discover that the logarithm will be a number between what? 1 and 3. Now, if I have a number like 245, you see that 245 is between what? 100 and what? 1000. So you see that the logarithm must fall between what? 2 and 3. So you see what I have? For that answer, I had what? 2 points. Do you get it? So as you begin to move from one group to the other, begin to have an idea of what the answer will likely be. So I'm just using this band to show you that what we have done is correct. All right. So before we call it off today, we're going to now see how we're going to use these concepts now to describe another idea. I'm going to clean this part of my board because that's where I want to, because I'll be needing these problems I've solved to drive this last idea. Now, if I have the log has 2 parts. Any log, let's pick this answer we have gotten here, the log of what? 34.34. So log of 34.34 is equal to 1.5358. I see that. Now, that is what we have. So this logarithm we have here is going to have two parts. There is a part we call the integer part. There's a part we call the decimal part. There's a part we call the integer part, and there's a part we call the decimal part. When we begin to go deeper, we'll explain some of these things better. We know that an integer can be what? Positive or negative. That means this part can be positive or it can be what? Negative. Take note of that because we're going to show some ideas on this much later. Now, this part is what we call the characteristic. And this part is the part we call the mantissa. We call this the characteristic and we call this the mantissa. Now, the mantissa part you get from your four-figure table. The characteristic part you get by writing in standard form. So the number of movements you have made for any number is the characteristics of that logarithm. While what you read out from your four-figure table is called the mantissa part. So take note of that because you need to understand that there's really nothing in this matter of logarithm. I've discovered over the years that it's best to take logarithm from the concept of standard form. Once you can write any number in a standard form, then solving logarithm will not be an issue at all. So you get this from writing your number in standard form, either physically or mentally. And then you get the mantissa part or the decimal part by doing what? Reading it from your four-figure table. Okay, we're going to take a question from page 21, exercise 1H, question 4. Page 21, exercise 1H, question 4. It says, express the following numbers in standard form and then write down the integer part of their logarithm. This one is a very straightforward exercise. Now look at that. So let's say I'm doing 4A. It says 6.5. This will give me, this is already a unit decimal. So this will be 6.5 times 10 to the power of what? 0. So the integer part, so characteristic integer part. Now they may say integer part or they may say, what is the characteristics? So they can say integer or characteristic. So it means the same thing. So they say the integer part will be equal to what? 0. That's all. But I'm going to stretch this question by asking you to do what? So for question 4 now, stretch it and do this for me. Find the integer parts and the mantissa or the decimal part. How would you do that? It means you need to go to your four-figure table and check for 6.5. We said that when you're checking your four-figure table, use the first 2 digits. So 6.5 will mean what? You're going to check 65 under 0. And if you check your four-figure table, 65 under 0 will be 8129, which will be what? 0.8129. So the log of 6.5 will be equal to 0.8129. So it means that the decimal part is going to be this, and the characteristic or the integer part will be this. So this is the much we will take this morning. In our next class or next meeting, we'll build up on this. But as a way of assignment, I want you to look at, that's in exercise 1H, look at question 4 and question 4 and question 7. Question 4 and question 7.